force voltage. So we are having the two type of analogy. One is a force voltage analogy, another one is a force current analogy. Okay. So the force voltage analogy is we are converting a force into the voltage equivalent, and if it is a force current analogy, the forces is converted into the current equivalent. Okay. So in the force voltage analogy, the three elements what we already discussed is replaced with help of the electrical equivalent components. So in a force voltage analogy, the force is equivalent to is a voltage, and the next one is the displacement. The displacement in a this is a mechanical system, mechanical, and this is a electrical parameter. Okay, so the force is equivalent is voltage, and the displacement is equivalent to it is charge, and dx by dt, which is a velocity. So the velocity is dx by dt, which is nothing but current. Okay, it is a rate of change of charge. Okay, and the three components we have to write the equivalent for these three components. So first one is a B. So the B is equivalent is dashpot equivalent is resistance, and for a mass it is equivalent in an electrical system is L, that is a inductance, and for a spring K the equivalent is it is called as a the inverse of capacitance. Okay, so this, if you know this one, we can convert this electrical system in terms of electrical equations. Okay, so from the equation 1 and 2, so this is for to deriving this force voltage analogy. So from the equations, from the diagram we can derive the equation 1 and 2, which will describe the mechanical equations of the system, and we can convert this equations into the equivalent force voltage terms. Okay, so for example, so if you take this force voltage analogy into this system, so we can follow the same steps. We can derive the mass balance equation at M1, and we can derive this equation. Okay, so after getting this equation, so we can convert. So in terms of velocity, it is called velocity is represented by current. Okay, so we can convert this equation into in terms of velocity. So it is m into dv by dt. So and this is a b into v. So we can convert the equivalent into in terms of I. Okay, so the force voltage analogy and force current analogy for the equation can be derived for this diagram. Okay, so for M1, if you consider this equation, so I am going to convert this the given equation in terms of velocity. So you know that dx by dt is a velocity. Okay, so the same way that is dy by dt if you take it, and acceleration is d square y by dt square. Okay, which is nothing but dv by dt. Okay, so you know this is the basics. So if you substitute here, so you'll get the equation will become m into dv by dt plus b into v plus k1 into y1 plus k2 into y1 minus y2 equal to f. Okay, so we can write the force voltage analogy of this equation, because we can easily convert in terms of voltage. Okay, so the mass is replaced by L, and the dv by dt. Okay, so the dv by dt, which is nothing but it is di by L into di by dt, plus the b is replaced by resistance R, and v is nothing but I. So it is I plus K1 is nothing but, so we can write here M1. So M1 is L1 and B is R and K1 is 1 by C1 and K2 is 1 by C2. Okay, so these are the terms we need. Okay, so from this one we can easily write this equation. So R into B is R into I, K1 is 1 by C1 into your Y1 is nothing but the displacement is charge. Okay, so the Y1 in terms of equation is, it is 1 by C1 into dq by dt, or charge in terms of current is so 1 by C1 into it is a Q plus Q1. So K2 is 1 by C2 into Q1 minus Q2 equal to, and the force is nothing but the voltage. Okay, so this is the electrical voltage analogy of the equation 1. Okay, so you can draw the diagram for this equation. So this equation is, you are having the first loop, you are having the resistance, inductance and capacitance. In a second loop commonly you are having C2. Okay, so we can draw the equation as, so first L1 and resistance and capacitance which is connected in series in the first loop, and in the second loop the commonly we are having the common element is K2. So that means it is 1 by C2 is a common element, so it is a C2 is connected here. This is a C1 and L into L1 R, and you will get the equation is C2 and Q1 minus Q2. You are having the second element is having the, so the common is K. So this is the electrical voltage analogy of the first, here the voltage V source. Okay, so from the second equation, so we derived the second equation from for a free body diagram for M2. So we have derived the second equation as this one. So before taking the Laplace transform, this is our the equation. So we can write the, again after that we are writing the free body diagram for mass M2. So again we are drawing the same free body diagram. So we are getting this equation. So again this equation is converted into electrical equivalent. So how you have to convert is, here we are going to again substitute in the same way. So you can write it M2. So here it is M2. So okay, M2 is equivalent is L2 and K2 equivalent is 1 by C2. Okay, so from the force voltage analogy, so substitute here. So you will get K2 is 1 by C2 into Q2 minus Q1 plus M2 is L2 into the d square y by dt square in terms of velocity is, again it is dv by dt. So you will get dv by dt is L into di by dt, which is equal to 0. Okay, so again if you writing the force voltage analogy of the equation, then you will get the common equation here is L2. So the total free body or the total diagram after converting into electrical system is, so this is from the equation 1 and the common element is C2, and in the second loop we are having the mass L2. So here you are having the L2 with the source may be given in the first block. So we are connecting the source here, the voltage source connected in the first loop. So because it is connected with the first mass, so this is the first free body diagram and the second free body diagram L2. Okay, so this is the electrical equivalent circuit of your mechanical system. Okay, is it clear? So we can derive the mathematical equation as well as force voltage analogy and force current analogy of this mechanical system. The same can be applicable for the rotational system, where the displacement is represented in a theta and force is represented in terms of torque. So that is a difference. The remaining things are same. Okay, thank you.